Okay, so we'll now look at the breadth first search algorithm that will be used to traverse the vertices of a graph. There are a lot of applications of breadth first search, and we will see one by one, a couple of them in this module, and a few more in the later modules. So it's a very important graph theory algorithm. We'll try to understand breadth first search using an example, and then we'll come back to pseudocode. Um, so basically, you're in a graph. You want to start with one vertex and then go traverse through the edges to reach the other vertices in the graph. And with breadth first search, you could find what is called the distance or the level numbers of the vertices from the starting vertex. So we start with, say, we could start with any vertex, but as a convention, if I do not state it, you could start with the vertex with the lower ID. So the starting vertex is also called the root of the breadth first search tree that will eventually you're going to find. So the level number of the root is said to be 0. So as I said, the level number is a measure of the distance. So the distance from the root to itself is 0. And initially we don't know the distance to the other vertices in the graph, so we set their level numbers to infinity. Now we also maintain a data structure called queue. The queue operates in first in first out fashion. So we use this queue to keep track of the vertices whose neighborhood is to be explored. So to begin with, we add vertex 1, the starting vertex, to this queue. So these are the things that we do as part of the initialization step. So if you go back to a pseudocode, you have a queue declared here, and you enqueue the starting vertex s to the queue. We set the level number of s to 0 and the level numbers of the other vertices to infinity, which means we don't know. And we also have a boolean flag for each vertex to indicate whether the vertex has been visited as part of the breadth first search or not. So for everyone other than the starting vertex s, we set this boolean visited to be false, and for the starting vertex x, it is set to true. So in this example, we'll use the color coding to indicate the visited thing. So for vertex 1, we code it as yellow to indicate it has been visited. The other vertices are not yet colored in yellow to indicate that they have been visited, so they are not visited yet. So these are things that you do in the initialization. So now get inside the loop, you go through series of iterations. In each iteration, what you do is, and of course you can do an iteration only if the queue is not empty. So if the queue is not empty, get inside the loop, which means to start a new iteration. And in each iteration, this is what you do: you dequeue the queue, and let us call the vertex you dequeued as vertex u. And now you're going to explore the neighborhood of vertex u. So you pick some neighbor, or not some neighbor, you pick every neighbor that has not yet been visited. So if visited of v is false, so if a neighbor has not been visited, now you mark it as been visited. You set its level number to be the one more than the level number of vertex u, and you also enqueue that neighbor vertex to the queue, and you also classify the edge between that vertex u and v as a tree edge. So if you're visiting a vertex for the first time, you classify the edge as a tree edge. Now if the neighbor v has been already visited, you don't do anything like this, other than just classifying the edge between u and v as a cross edge. So let's see what we do here. So for vertex 1, it has 3 neighbors, 2, 3 and 7. Now none of them have been visited, so you can visit each of these neighbors. So you color code them to be yellow, and the level number of each of these is one more than the level number of the vertex u, which is vertex 1, the starting vertex. And you label these edges as tree edges because 2, 3 and 7 are visited for the first time. And you also enqueue them to the queue. So you dequeued the queue, so the queue is initially or temporarily empty during this iteration, and now you enqueue 2, 3 and 7. You could enqueue them in any order, but we're just going to following the convention of adding the neighbors in the increasing order of their IDs. So 2, 3, 7 are the neighbors that you're exploring. So enqueue them in the order of the IDs. So now that's one iteration. So now second iteration, you dequeue the queue, so 2 comes out of the queue, and now you explore the neighbors of 2. So for 2, 4 and 7 are the neighbors. 4 has not been visited yet, so you mark it as visited, set the level number of 4 to be 1 more than the level number of 2, so 1 plus 1, 2, label this edge as tree edge. And now 7 has been already visited, so you label this edge as what is called a cross edge. So if your neighbor that you're trying to explore has been already visited, you label that edge as a cross edge. Otherwise, you label the edge as a tree edge, set the level number of that neighbor to be 1 more than the level number of the vertex you're trying to visit from. And what else? Mark that neighbor has been visited now, and then also add that neighbor to the queue. So 7 is since already visited, you don't need to add 7 to the queue, but 4 has not been visited before, so you enqueue 4 to the queue. So 2 is dequeued, the queue is temporarily 3 and 7. Now you add 4 to it. So continue the process. Now dequeue the queue. So 3 comes out of the queue. The neighbors of the 3 are 4 and 5. Of course, 1 is also a neighbor, but 1 has been already visited and the edge has been classified also. So now 4 has been already visited, so you label the edge as a cross edge. Now 5 has not been visited, so first mark 5 has been visited, set its level number as 1 more than the level number of 3. So 1 plus 1, 2, label the edge as a tree edge and add 5 to the queue. So 3 is out of the queue, 7, 4 and now 5 are the queue. So 7 is the next vertex to be dequeued, but both the edges associated with 7 have all been already classified, so we don't have to do anything. So then that's one iteration actually. So 7 has been dequeued. Now 4 and 5 are in the queue. Now explore the neighbors of 4, which are 5 and 6. Now 5 has been already visited, so you have to just label this edge as a cross edge. And 6 has been not visited, so mark 6 has been visited now, label the edge as a tree edge, set its level number as 1 more than the level number of 4, so it's 2 plus 1, 3, and mark this edge as a tree edge. So now 4 is out of the queue, 5 and 6 are in the queue. Now for 5, this edge to 6 has been not classified yet, but 6 has been already visited, so this edge is now a cross edge, and that's it here too. So then 6 is alone in the queue, dequeue it, all its associated edges are already classified, so you don't have to do anything, the queue becomes empty. So basically you go through the iterations until the queue becomes empty. Okay. Now as you see, if you start from say vertex 1 and you were able to reach all the vertices, or if you start from some vertex and basically be able to reach all the vertices and before the queue becomes empty, then it's basically the question of reachability. So from that starting vertex you're able to reach the other vertices. And since it's an undirected graph, it also means that you can basically reach from any vertex to any other vertex in the graph. So the graph is said to be connected. Okay. So to test for connectivity of a graph, you could use breadth first search. You could start from some vertex and just check if you're able to reach other vertices. And since it's an undirected graph, it also means that from any vertex you can reach any other vertex. Okay. Now if you start breadth first search from some vertex and you're not able to reach all the vertices, like this, in this case, this is a graph of 8 vertices. Start from 1 and you're able to reach only 2, 3, 4, 5, 6. So whatever you do, you cannot reach 7 and 8 when you're doing breadth first search from 1. So you have to start again breadth first search for 7 and then reach 8. So in this case we can say that the whole graph of 8 vertices is not connected because you started breadth first search from some vertex and you are able to reach only 6 vertices totally, including a starting vertex. So 1, 2, 3, 4, 5, 6 are said to be part of what is called a component. 7 and 8 are also part of a component. So there are two components in this graph. So if a graph is connected like this, all vertices are reachable to each other, so we say the whole graph is in one single component. On the other hand, if you are not able to reach all the vertices in one instance of breadth first search, then the graph is said to be not connected, and you can really find each of the components by running breadth first search from any vertex in that component. So this graph has two components, and this graph, all the vertices are said to be in one component. Okay, so you can, this is one application of breadth first search. You can check for connectivity of the graph and also be able to find the vertices that are part of a component. So a component by definition, later we'll use this also for a cluster, is second of the largest subset of vertices, is that if you add any more vertex to this set, then the vertices are not reachable to each other. Okay, so you can say I can claim 3, 4, 5, 6 is a component because the vertices are reachable to each other. But when you add 1 or 2 or even both to this set, 1 and 2 are also reachable to 3, 4, 5, 6. So now when you add 7 to this set of 6 vertices, you can find 7 is not reachable to 1, 2, 3, 4, 5, 6 or 8. So we can claim that 1, 2, 3, 4, 5, 6 constitute the largest set of vertices that are reachable to each other. So they are forming a component. And 7 and 8 is also a largest set of vertices that are reachable to each other. I cannot add any more vertex to this set 7 and 8 and make them reachable to each other. So 7 and 8 also will be considered as a component. Okay. Now in the graph below, all the 8 vertices are considered as one component because they are reachable to each other. So that's the largest set of vertices that are reachable to each other. Alright, so another application of breadth first search is this. Given a graph, we can use the results of breadth first search that we just saw to decide whether the graph is bipartite or not. Now, a bipartite graph is basically a graph in which you can partition the set of vertices into two sets. Now, they need not be equal in size like this. They could be like one partition or set has just one vertex or two vertex, and the other partition has all the other vertices. So it's also possible. So a bipartite graph has two disjoint set of vertices, means any vertex can be in only one of the two partitions, and all the edges in the graph, so this is important condition, all the edges in the graph should be between vertices in the two partitions. That means there should not be any edge between vertices in the same partition. So if a graph satisfies this requirement or property, it can be called a bipartite graph. Now how would it check whether a given graph is bipartite or not using the results of breadth first search? Now the rule is this. There should not be any cross edges between vertices at the same level. So if a graph does not have any cross edges between vertices at the same level, then it could be called a bipartite graph. Now remember, the rule states explicitly that there are no cross edges between vertices at the same level. That means there could be cross edges between vertices at different levels, and such a graph could be called a bipartite graph. So as long as there are no cross edges between vertices at the same level, the graph could be called bipartite. So we could use these results here to decide whether the graph is bipartite or not. So look mainly for cross edges and check for every cross edge the vertices are between the same level or not. Now here this cross edge has the two vertices 2 and 7 at the same level. Now just because this property is violated for this particular edge, we can just rule out and say the whole graph is not bipartite. So if the graph is bipartite, this rule has to be applicable for all the cross edges. Okay. So there is one more example here for breadth first search I have shown here. So again I have shown here the starting vertex, say which is 1. You could do any other vertex also for practice. I recommend you to try that. So start with 1. So push it to the, or sorry, add it to the queue. Mark it has been visited and its level number is 0. So from 1 you can visit the neighbors 2, 3 and 7. So all those 3 neighbors will be marked visited, and they are added to the queue, as well as the level numbers are said to be 1 more than the level number of the vertex from which you visit them. So it is going to be 0 plus 1 is 1 and so on. So now the queue has 2, 3, 7. So DQ the queue. So 2 comes out of the queue, 4 and 8 are its neighbors. Both have not been visited, so mark them as visited and label the edges as 3 edges and set the level numbers to be 1 more than the level number of node 2, which will be 2 and 2, 4 and 8. Also add 4 and 8 to the queue. So the queue currently has 3, 7, 4, 8. So DQ and 3 comes out of the queue. 4 is already in the queue, so the only neighbor that has not been visited yet is vertex 5. So label the edge as a 3 edge, mark it has been visited, set its level number to be 1 more than the level number of node 3, so it becomes 2. So add 5 to the queue, 3 is out of the queue, so 7, 4, 8, 5 are in the queue. Now 4 is a neighbor that has been already visited, so label the edge between 3 and 4 as a cross edge. So now DQ the Q7 comes out of the queue. So the neighbor 8 has been marked, but the edge has not been classified yet, so it should be now marked as a cross edge. There are no other neighbors to be edge visited, or the associated edge not classified. So now when then 7 is removed from the queue, 4 is now in the beginning of the queue. Now it has 6 and unvisited neighbors so far, so mark it 6 has been visited, label its weight as 2 plus 1. 2 is the level number of 4, visiting 6 from 4. So the level number of 6 is going to be 2 plus 1, which is 3. So now add 6 to the queue. So 4 is out of the queue has 8, 5 and 6. So 8 is in the head of the queue, and so you can remove 8, label 8 as being visited. 8 is the head of the queue, so DQ 8. Now both its associated edges are already classified. The edge to 2 is a 3 edge, edge to 7 is a cross edge, so it cannot do anything. DQ 5. Now this edge to 6 should be called a cross edge because 6 has been already visited, and that's what we can do for 5. So DQ5. Now for 6 we DQ6 because we don't need to do anything else. So this is the final result of breadth first search, and these are the level numbers. Now we want to check whether this graph is bipartite or not. So just check the level numbers or the cross edge vertices. So 7, 8 on 2 different level numbers, fine. 3, 4, 2 different level numbers. 2, 3, 2 different level numbers. So because of this, the property being satisfied, we can claim this to be a bipartite graph. And the 2 partitions are just based on the level numbers. The vertices that are the even level number are in one partition, the vertices with the odd level numbers on the other partition. So in this result here, the vertices with even level numbers are 0, 5, 8, 4 and 6. Not 0, 1, 5, 8, 4 and sorry, I made a mistake. So the vertices with even level numbers. So even numbers are 0, 2, 2 and 2. So the corresponding vertex IDs are 1, 5, 8 and 4. So these are the 4 vertices at even level. The vertices at odd level are 3, 7, 2 and 6. So the vertices with even level numbers 1, 4, 5 and 8. The vertices with odd level numbers are 2, 3, 6 and 7. Now just put together the edges in this graph on this partition visualization. Now we can notice that all the edges are between vertices in the two partitions. So for example, one has edge with 2, 3 and 7, so one has edge with 2, 3 and 7. 2 has edge with 1, 8, 4 and 8, so 2 has edge with 1, 4 and 8. So all the edges will be between vertices in the two different partitions. Again, remember, the two partitions could be of different size, need not be always the same size. Okay, so with this we can stop this video.